Imagine reality as a video game with a resolution limit. This isn't just a wild hypothesis. It's an idea that emerges from the fundamental incompatibility between our two most successful theories of the universe: Albert Einstein's general relativity and quantum mechanics. For centuries, our understanding of space and time has largely been rooted in the concept of a smooth, continuous backdrop against which events unfold. This classical view, solidified by Newton and then dramatically reshaped by Einstein, paints a picture where you can always divide any distance or any interval of time into smaller and smaller pieces infinitely. It's like a perfectly smooth canvas, allowing for an endless resolution of detail. However, this intuitive notion of smoothness faces a serious challenge when we delve into the quantum realm, the bizarre world of the very small. At the heart of the pixelated spacetime concept is the Planck length, an incredibly tiny unit of distance. To give you a sense of just how small it is, imagine an atom. Now imagine something 100,000 times smaller than that. The Planck length is still about 10 million trillion times smaller than even that minuscule size, approximately 1.6 times 10 to the power of -35 meters. It's so small that if you were to enlarge a space-time pixel to the size of a grain of sand, an atom would be as large as a galaxy. This isn't just an arbitrary number. It's derived from fundamental constants of nature: the speed of light, Planck's constant, from quantum mechanics, and the gravitational constant from general relativity. It represents the scale at which the smooth, continuous geometry of space-time, as described by general relativity, is expected to break down. The idea of a pixelated or discrete space-time isn't entirely new. Werner Heisenberg, one of the pioneers of quantum mechanics in the 1920s, suggested that space and time might be pixelated into indivisible units at the Planck length. While this was a radical idea at the time, it has gained significant traction among scientists today. The mathematical frameworks of quantum mechanics often point towards a reality that is fundamentally discrete, where quantities like energy and momentum exist in distinct packets or quanta. If everything else is quantized, why should space and time be any different? This leads us to the concept of quantum foam, a term coined by physicist John Wheeler in 1955. Wheeler proposed that at these unimaginably small scales, space-time isn't calm and smooth. Instead, it's a turbulent, frothing sea of quantum fluctuations. Imagine the surface of a rapidly boiling pot, with bubbles constantly appearing and disappearing. That's a crude analogy for quantum foam, where virtual particles of matter and antimatter are constantly created and annihilated, distorting the very geometry of space-time itself. These fluctuations are a direct consequence of Heisenberg's uncertainty principle applied to energy and time, meaning that over extremely short intervals, large energy fluctuations are permitted, and these fluctuations, through mass-energy equivalence, curve spacetime. The implications of such a pixelated or foamy spacetime are profound. If spacetime is discrete, then motion through it wouldn't be perfectly smooth. It would involve tiny, discontinuous jumps, much like a computer simulation. While we wouldn't perceive these jumps in our everyday lives, because we operate on scales vastly larger than the Planck length, it fundamentally changes our understanding of reality. It suggests that there's a fundamental minimum size below which space-time loses its conventional meaning. The illusion of smoothness is compelling because, on our macroscopic scales, space-time appears continuous. Just as a digital image, when viewed from a distance, seems perfectly smooth, it reveals its individual pixels only upon extreme magnification. Similarly, the seemingly seamless flow of time and the continuous expanse of space might be an emergent property, arising from the collective behavior of countless discrete, fundamental units. Think of sand dunes. From afar, they look smooth, but up close, you see individual grains. This pixelation isn't just a theoretical curiosity, It's a crucial aspect of the quest for a theory of quantum gravity. Our current understanding of physics is built upon two pillars: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. The problem is, these two theories are fundamentally incompatible. General relativity assumes a smooth, continuous spacetime, while quantum mechanics thrives in a discrete, probabilistic, particle-based framework. When physicists try to apply quantum mechanics to gravity, especially in extreme environments like black holes or the very early universe, the equations break down, leading to mathematical inconsistencies and infinities. This breakdown signals that our current understanding is incomplete and that a deeper, unified theory is needed. The idea of pixelated spacetime offers a potential path forward, suggesting that at the most fundamental level, gravity itself might be quantized, just like other forces. Now, let's step back and appreciate the magnificent framework that has shaped our understanding of gravity for over a century: Einstein's general relativity. Imagine spacetime not as a static, rigid stage upon which cosmic events unfold, but as a dynamic, flexible fabric, a four-dimensional tapestry woven from 3 dimensions of space and 1 of time. This revolutionary concept, unveiled by Albert Einstein in 1915, fundamentally reshaped our perception of gravity. Prior to Einstein, Isaac Newton's law of universal gravitation, while incredibly successful in describing the motion of planets and falling apples, presented gravity as a mysterious force acting instantaneously across vast distances. It was a force without a mediator, an action at a distance that even Newton himself found perplexing. Einstein, however, offered a profoundly different and more elegant explanation. In general relativity, gravity isn't a force pulling objects together. Rather, it's a manifestation of the curvature of spacetime itself. Think of a bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip or curvature in the sheet. If you then roll a marble across the sheet, its path will be deflected by this curvature, appearing to be pulled towards the bowling ball. In this analogy, the bowling ball represents a massive object like a star or a planet, and the marble represents another object, or even light, moving through its vicinity. The mass and energy of objects warp the fabric of space-time around them, and this curvature dictates how other objects move. Planets orbit the sun not because they are being pulled by an invisible force, but because they are following the curves in space-time created by the sun's immense mass. Light, too, follows these curves, which is why massive objects can bend light, a phenomenon known as gravitational lensing. This prediction was famously confirmed during a solar eclipse in 1919 by Arthur Eddington's expedition, which observed stars seemingly shifted from their usual positions due to the sun's gravity bending their light. This empirical evidence catapulted Einstein to international fame and solidified general relativity as the prevailing theory of gravity. A cornerstone of general relativity is its description of spacetime as continuous and smooth. There are no gaps, no discrete units, no fundamental pixels in Einstein's universe. Instead, spacetime is envisioned as an infinitely divisible continuum, much like the surface of a perfectly smooth, unblemished sphere. You can zoom in on any point, and you'll always find more space, more time, without ever hitting a fundamental limit or a granular structure. This continuity is mathematically represented by differential geometry, a branch of mathematics that deals with smooth curves, surfaces, and spaces. The equations of general relativity, known as Einstein's field equations, describe how the distribution of mass and energy determines the geometry of spacetime, and conversely, how this geometry dictates the motion of matter and energy. These equations are incredibly powerful, allowing us to accurately predict phenomena ranging from the orbits of planets to the expansion of the universe and the behavior of black holes. The concept of continuous spacetime has profound implications. It suggests that space and time are not merely passive backgrounds, but active participants in the cosmic drama. They can be stretched, squeezed, and warped by the presence of matter and energy. This dynamic interplay is what gives rise to gravity. For instance, the expansion of the universe, observed by Edwin Hubble, is not merely galaxies moving through a static space. It's the fabric of space-time itself stretching, carrying the galaxies along with it. Similarly, gravitational waves, ripples in space-time generated by accelerating massive objects like colliding black holes, are a direct consequence of this dynamic, continuous nature. The detection of gravitational waves by the LIGO experiment in 2015 provided yet another spectacular confirmation of Einstein's theory, opening a new window into the universe. Within this continuous framework, general relativity has successfully described some of the most extreme environments in the cosmos. Black holes, for example, are regions of space-time where gravity is so intense that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. Inside this horizon, space-time is so severely warped that all paths lead inward to a singularity, a point of infinite density and curvature. According to general relativity, at the singularity, the laws of physics as we know them break down. Similarly, general relativity provides the theoretical underpinning for our understanding of the Big Bang, the prevailing cosmological model for the universe's earliest moments. It describes how the universe began from an extremely hot, dense state and has been expanding and cooling ever since. However, despite its immense success, general relativity, with its continuous spacetime, faces significant challenges when confronted with the quantum realm. The smooth, infinitely divisible nature of spacetime in general relativity stands in stark contrast to the quantized, discrete nature of everything else in the universe at the microscopic level. This fundamental incompatibility becomes particularly acute when trying to describe phenomena where both gravity and quantum effects are significant, such as at the heart of black holes or during the very first moments of the universe. The theory's reliance on a continuous spacetime leads to mathematical infinities when attempting to merge it with quantum mechanics, signaling a fundamental incompleteness. It's like trying to describe a digital image using only the mathematics of continuous functions. You're missing the underlying pixelated structure. The idea of pixelated spacetime, therefore, emerges as a compelling alternative, suggesting that the smooth canvas of Einstein's universe might, at its most fundamental level, be composed of discrete, indivisible units, much like the pixels on a screen. This radical notion offers a potential bridge between the two great pillars of modern physics, hinting at a universe that is far more granular and interconnected than we currently perceive. The quantum realm is a place of profound strangeness, where the familiar rules of classical physics break down entirely and a new, often counterintuitive, set of principles takes over. This is the domain of the very small, atoms, electrons, photons, and other subatomic particles, where the fundamental building blocks of reality engage in a dance that shapes everything we see and touch. One of the most mind-bending concepts in quantum mechanics is wave-particle duality. It states that particles, such as electrons and photons, can behave as both particles and waves depending on how they are observed. Light, for instance, exhibits wave-like properties, creating interference patterns similar to ripples on water, which explains phenomena like diffraction. Yet, in other experiments, like the photoelectric effect, light behaves as discrete packets of energy called photons, acting like particles. This dual nature was famously demonstrated by the double-slit experiment, where even single electrons, or photons, when unobserved, appear to pass through both slits simultaneously as a wave, only to collapse into a definite particle state upon measurement, creating an interference pattern over time. This paradoxical behavior lies at the heart of quantum physics, challenging our classical understanding of what a particle or a wave truly is. Another cornerstone of the quantum realm is the Heisenberg uncertainty principle, introduced by Werner Heisenberg in 1927. This principle asserts that there are inherent limits to the precision with which certain pairs of physical properties of a particle, known as conjugate variables, can be simultaneously known. The most common example is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments. It's a fundamental property of nature itself, stemming from the wave-like behavior of quantum objects. If you try to pinpoint the exact location of an electron, its velocity becomes wild and indeterminate. This principle also applies to other conjugate pairs, such as energy and time, meaning you cannot measure the precise energy of a system in a finite amount of time. The uncertainty principle profoundly challenges the classical Newtonian view, which held that all variables of a particle could be known to exact precision simultaneously. Then there's quantum superposition, a concept that truly defies our everyday intuition. It states that a quantum system, like an electron or a photon, can exist in multiple possible states at the same time, rather than being confined to a single definite state. Imagine a flipped coin spinning in the air. Classically, it's either heads or tails, even if we don't know which. In the quantum world, however, a particle in superposition is genuinely in all its possible states simultaneously until a measurement forces it to collapse into one specific state. The most famous illustration of this is Schrödinger's cat, a thought experiment where a cat in a sealed box, linked to a quantum event, is considered simultaneously both alive and dead until the box is opened and observed. While this seems absurd for macroscopic objects, superposition is a very real phenomenon for quantum particles and is a foundational principle for emerging technologies like quantum computing. Perhaps the most enigmatic of quantum phenomena is quantum entanglement. This occurs when two or more quantum particles become linked in such a way that the quantum state of each particle cannot be described independently of the others, even when they are separated by vast distances. A change to one entangled particle seems to instantaneously influence the other, no matter how far apart they are. A connection Albert Einstein famously dubbed spooky action at a distance. This doesn't involve any signal traveling between the particles. Instead, the entangled system behaves like a single, unified whole. Experiments have repeatedly confirmed the reality of quantum entanglement, showing that these correlations cannot be explained by any hidden local variables. Entanglement is not just a theoretical curiosity. It underpins new technologies in quantum computing and secure communications. These bizarre behaviors, wave-particle duality, the uncertainty principle, superposition, and entanglement, are not just abstract theoretical constructs. They have been confirmed by countless experiments and are the bedrock of quantum mechanics, a branch of physics developed by pioneers like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg, among many others, in the early 20th century to explain observations that classical physics simply could not. Quantum mechanics provides the mathematical framework for describing the behavior and interactions of particles at these incredibly small scales, forming the cornerstone of the standard model of particle physics, which encompasses the electromagnetic, weak, and strong nuclear forces. Quantum field theory further extends these ideas, describing particles as excitations of quantum fields. The quantum realm is not a different place, but rather a different way of looking at why things are the way they are. While Newton's equations perfectly describe the macroscopic world of falling apples and orbiting planets, they break down at the atomic and subatomic scales. Understanding the quantum realm is crucial because it underlies most things in the modern world, from the functioning of lasers and semiconductors to the development of MRI machines and drug design. It challenges our traditional understanding of reality, suggesting that outcomes are probabilistic rather than certain, and that physical quantities are quantized, meaning they can only take on specific, discrete values. This probabilistic nature, where the outcome is undetermined until a measurement is performed, makes quantum mechanics an inherently probabilistic theory. The profound implications of these principles continue to reshape our understanding of the universe and our place within it, hinting at a reality that is far more nuanced and interconnected than the continuous, predictable world we experience directly. The profound implications of these principles continue to reshape our understanding of the universe and our place within it, hinting at a reality that is far more nuanced and interconnected than the continuous, predictable world we experience directly. This brings us to one of the most significant and enduring challenges in theoretical physics, the grand challenge of reconciling gravity and quantum mechanics. For over a century, these two monumental theories, Albert Einstein's general relativity and quantum mechanics, have stood as the twin pillars of modern physics, each describing their respective domains with astonishing accuracy. General relativity, formulated in 1915, beautifully explains gravity as the curvature of a smooth, continuous spacetime caused by mass and energy, governing the universe on its largest scales, from the orbits of planets to the dynamics of galaxies. In stark contrast, quantum mechanics, developed in the early 20th century, describes the probabilistic and discrete behavior of matter and energy at the smallest scales, where particles can exist in multiple places at once and interactions are mediated by the exchange of discrete quanta. The problem isn't that one theory is wrong. Both have been exhaustively tested and proven remarkably accurate within their specific realms. The conflict arises when we attempt to apply both theories simultaneously to extreme environments where both gravitational and quantum effects are significant. These are the enigmatic frontiers of physics, the heart of a black hole, where matter is crushed to an unimaginable density, or the fleeting moments immediately after the Big Bang, when the entire universe was compressed into an infinitesimally small, incredibly hot state. In these scenarios, the equations of general relativity break down, yielding nonsensical infinities, and the probabilistic nature of quantum mechanics clashes fundamentally with the smooth, deterministic fabric of spacetime described by Einstein. One of the core incompatibilities lies in their fundamental descriptions of spacetime. General relativity necessitates a smooth, continuous spacetime where gravity is a geometric phenomenon, a warping of this fabric. Quantum mechanics, however, thrives in a discrete, particle-based framework, suggesting that at incredibly small scales, spacetime itself might not be continuous, but rather chunky or pixelated, undergoing quantum fluctuations so strong that our ordinary notions of space and time lose their meaning. Imagine trying to describe the ripples on a pond, gravity, while simultaneously acknowledging that the pond itself is made of individual, discrete water molecules, quantum mechanics. The two descriptions, while individually valid, don't easily mesh. Furthermore, quantum field theory, which successfully unifies quantum mechanics with special relativity to describe the electromagnetic, strong, and weak forces, explains force interactions through the exchange of well-defined quanta, or messenger particles. For gravity, the hypothetical messenger particle is the graviton. While it's possible to formulate a quantum theory of graviton exchange, this approach faces a significant hurdle: non-renormalizability. In simpler terms, when physicists try to calculate gravitational interactions at very high energies using quantum field theory, they encounter an infinite number of parameters, leading to calculations that produce infinite values for physical quantities, making the theory mathematically inconsistent and non-predictive at the Planck scale. This is a fundamental roadblock that has plagued physicists for decades, unlike the other fundamental forces which are renormalizable. Another profound point of tension is the problem of time. Quantum mechanics typically assumes a universal and absolute flow of time, a fixed background against which events unfold. General relativity, on the other hand, reveals time as a dynamic, malleable entity, interwoven with space to form spacetime, whose flow is relative and influenced by gravity. This relativistic nature of time, where its passage can vary depending on an observer's motion and gravitational field, directly conflicts with the absolute time often presumed in standard quantum formulations. What then is time in a truly unified theory? Is it a fundamental, distinct phenomenon, or an emergent property of something deeper? The weakness of gravity compared to the other fundamental forces also presents a monumental experimental challenge. Gravity is incredibly feeble at the quantum scale, approximately 10 to the power of 40 times weaker than the electromagnetic force. This makes it extraordinarily difficult to experimentally observe any quantum gravitational effects, as they are expected to manifest only at the Planck length, an unimaginably small scale, around 10 to the power of negative 35 meters, or under conditions of extreme energy and density, such as those found within black holes or the very early universe. Our current technology is far from capable of directly probing these regimes. This lack of experimental data means that theoretical physicists are largely working without direct empirical guidance, making the development of a quantum theory of gravity an even more arduous task. The incompatibility also manifests in the breakdown of classical general relativity at singularities, points of infinite density and curvature, such as those predicted at the center of black holes or at the Big Bang. Here, the theory simply ceases to be predictive, signaling the need for a more complete description that incorporates quantum effects. Furthermore, the Heisenberg uncertainty principle, a cornerstone of quantum mechanics, states that we cannot simultaneously know with perfect accuracy both the position and momentum of a particle. This principle makes it unclear how to determine the gravitational field of a quantum particle, as its precise location and velocity cannot be known with certainty, further complicating attempts to merge the two theories. The quest to reconcile gravity and quantum mechanics is not merely an academic exercise. It is a pursuit of a deeper, more complete understanding of reality itself. It's about finding a single, coherent framework that can describe the universe from its smallest constituents to its grandest cosmic structures, from the quantum foam of space-time to the sprawling tapestry of galaxies. It's about resolving the paradoxes and inconsistencies that arise when these two highly successful but fundamentally different descriptions of nature are brought together. The stakes are immense, promising to unlock secrets about the origins of the universe, the true nature of black holes, and perhaps even the very definition of space and time. This grand challenge has spurred the development of radical new ideas, pushing the boundaries of human thought and demanding a profound rethinking of our most basic assumptions about the cosmos. One of the most compelling and rigorously developed approaches to this grand challenge is loop quantum gravity, or LQG. Unlike some other theories that attempt to embed gravity within an existing spacetime, LQG takes a radical stance. It postulates that spacetime itself is not a smooth, continuous backdrop, but rather a dynamic, granular entity woven from fundamental, finite loops. This is a profound departure from Einstein's continuous canvas, suggesting that if we could zoom in close enough, we would see spacetime pixelated, with a minimum length scale on the order of the Planck length, approximately 10 sup/35/sup meters. Below this scale, the very concept of space and time as we understand them would cease to have meaning. At its heart, LQG is an attempt to develop a quantum theory of gravity based directly on Einstein's geometric formulation of general relativity. It seeks to quantize gravity by quantizing spacetime itself, treating it as a network of interconnected loops. These networks are known as spin networks, and their evolution over time forms spin foams. The theory suggests that just as matter is composed of atoms, space itself has an atomic structure. This discreteness is a key feature, implying that quantities like area and volume are not infinitely divisible, but come in discrete packets. Imagine trying to measure the area of a surface. Instead of getting any possible value, LQG predicts that you would only find values that are integer multiples of a fundamental, tiny unit of area. This quantum discreteness of geometry is one of the most remarkable physical results derived from LQG. The development of LQG has a rich history, with significant contributions from physicists like Abbe Ushtaker, Carlo Rovelli, and Lee Smolin. Ushtaker's reformulation of general relativity in terms of new variables in the 1980s provided a crucial mathematical framework. This allowed for the application of quantum mechanics to gravity in a way that preserved the background independence of general relativity, meaning the theory doesn't rely on a pre-existing spacetime. Rovelli and Smolin then further developed the loop representation, leading to the discovery of the quantized nature of area and volume. One of the most significant implications of LQG is its potential to resolve the singularities predicted by general relativity. In Einstein's theory, singularities are points of infinite density and curvature, such as those found at the heart of black holes or at the Big Bang. At these points, the laws of physics as we know them break down. However, in LQG, the granular nature of spacetime prevents these infinities. Because space cannot be divided beyond the smallest tile or loop, gravity cannot become infinite. Instead of a singularity, LQG predicts a quantum bounce. For black holes, this means that instead of being crushed to an infinitely dense point, matter falling into a black hole would reach a point where quantum gravitational effects become dominant, preventing the singularity. Some models within LQG even suggest that black holes might transition into white holes, which are essentially the time reverse of black holes, expelling matter and energy. This bounce concept is also applied to the origin of the universe, where the Big Bang singularity is replaced by a big bounce, suggesting that our universe emerged from the collapse of a previous universe. This quantum bridge between contracting and expanding cosmological branches offers a new perspective on the universe's beginning and could potentially resolve issues like the horizon problem. The repulsive force generated by quantum geometry effects in LQG becomes dominant at the Planck scale, overcoming classical gravitational attraction and resolving these singularities. While LQG is a compelling framework, it is still a work in progress. The full dynamics of the theory are complex and remain an active area of research. There are different variants of the theory, such as canonical loop quantum gravity and spin foam theory, each exploring different aspects of its dynamics. A crucial aspect of any scientific theory is its testability. The Planck scale, where LQG effects are predicted to manifest, is incredibly small, making direct experimental verification extremely challenging with current technology. However, researchers are exploring various avenues for indirect evidence. For instance, loop quantum cosmology, LQC, a subfield of LQG, investigates the early universe and predicts observable signatures in the cosmic microwave background radiation, the afterglow of the Big Bounce. These signatures could manifest as specific patterns in the temperature fluctuations of the background radiation. Additionally, some theoretical models suggest that LQG could lead to observable phenomena around black holes, such as superradiation, which doesn't exist in traditional theories. There's even ongoing research into simulating LQG on photonic chips, aiming to provide predictions that could eventually be tested experimentally. Philosophically, LQG presents a radical shift in our understanding of reality. If space-time is fundamentally discrete and emergent, then our everyday experience of a continuous, flowing space and time is an illusion. It challenges the very notion of time as a fundamental entity, suggesting that change can occur without a continuous temporal backdrop. This radical process metaphysics emphasizes becoming over being, where the physical world is ever-changing yet timeless at a fundamental level. This background independence, where space-time is not a fixed stage but an active participant, is a core philosophical tenet of LQG. Compared to other approaches to quantum gravity, such as string theory, LQG takes a different path. While string theory posits that fundamental particles are tiny vibrating strings in higher dimensions and aims to unify all fundamental forces, LQG primarily focuses on quantizing gravity directly, based on general relativity. String theory often requires 10 dimensions, whereas LQG does not. These distinct starting points lead to different mathematical frameworks and physical predictions, highlighting the diverse and innovative thinking currently at play in the quest for a unified theory. The ongoing development of LQG, with its focus on the quantum nature of spacetime itself, represents a powerful and unique attempt to weave together the fabric of reality at its most fundamental level. While loop quantum gravity offers a compelling vision of a granular spacetime, another prominent contender in the quest for quantum gravity takes a radically different approach: string theory. Instead of point-like particles, string theory postulates that the fundamental constituents of the universe are not zero-dimensional points, but rather tiny, one-dimensional, string-like entities. Imagine these strings as incredibly small, vibrating filaments of energy, far too small to be observed directly with current technology, on the order of 10 sup-33/sup centimeters. The magic of string theory lies in the way these strings vibrate. Much like the different vibrational patterns of a violin string produce different musical notes, the various vibrational modes of these fundamental strings are thought to give rise to all the different particles we observe in nature, each with its unique properties like mass and charge. An electron, for instance, is simply a string vibrating in one particular pattern, while a quark is a string vibrating in another. Crucially, among these myriad vibrational patterns, string theory predicts the existence of a particle that mediates the gravitational force, the graviton. This is a profound achievement, as it naturally incorporates gravity into a quantum mechanical framework, a feat that has eluded physicists for decades when dealing with point-like particles. The ability of string theory to smear interactions over small distances, due to the strings having a length rather than being point-like, helps to resolve the inconsistencies that arise when trying to combine general relativity and quantum mechanics. In conventional quantum field theory, particles interact over zero distance in spacetime, which creates mathematical infinities when gravity is involved. Strings, by their very nature, avoid these problematic zero-distance interactions, smoothing out spacetime at the quantum level and allowing for a consistent description of gravity alongside the other fundamental forces. Indeed, one of the most ambitious goals of string theory is to provide a unified description of all fundamental forces and matter within a single quantum mechanical framework. This makes it a leading candidate for a theory of everything, a self-contained mathematical model that describes all fundamental forces and forms of matter. Beyond gravity, string theory aims to unify electromagnetism, the strong nuclear force, and the weak nuclear force, the four fundamental forces of nature, along with all types of matter. However, this elegant solution comes with a significant conceptual cost. String theory requires the existence of extra spatial dimensions beyond the three we perceive, plus the dimension of time. While we experience a four-dimensional spacetime, string theory often necessitates a universe with at least 10 or even 11 dimensions. The reason for these extra dimensions is rooted in the mathematical consistency of the theory. Trying to eliminate them leads to much more complicated equations. So, where are these extra dimensions? The prevailing idea is that they are compacted or curled up into unimaginably tiny sizes, far too small for us to detect directly. Imagine a garden hose. From a distance, it looks like a one-dimensional line. But if you were an ant crawling on its surface, you would discover a second, curled-up dimension around its circumference. Similarly, these extra dimensions are thought to be curled up at scales as small as the Planck length, making them imperceptible to our macroscopic world. The introduction of these higher dimensions has profound implications. For instance, in some string theory models, the force-carrying bosons of particle physics arise from open strings with endpoints attached to our familiar four-dimensional spacetime, while gravity arises from closed strings that can propagate through the larger, higher-dimensional space. This concept provides a natural explanation for why gravity is so much weaker than the other fundamental forces. The development of string theory has not been a linear path. Initially, various distinct string theories emerged, each with its own set of properties and requirements. However, in the mid-1990s, these seemingly disparate theories were found to be interconnected through a more encompassing framework known as M-theory, which operates in 11 dimensions. This unification suggested a deeper underlying structure and strengthened the hope for a single, consistent theory. Despite its mathematical elegance and potential to unify all forces, string theory faces significant challenges. The most prominent is the lack of direct experimental evidence. The energies required to probe the string scale are astronomically high, far beyond the capabilities of any current or foreseeable particle accelerator. An experiment to directly test string theory might require a collider the size of a galaxy. This has led some critics to question its scientific validity, arguing that a theory that cannot be empirically tested is more akin to philosophy or even theology. However, proponents argue that indirect evidence and theoretical consistency are compelling. String theory has contributed significantly to mathematical physics, offering insights into problems in black hole physics, early universe cosmology, and quantum gravity. Furthermore, recent theoretical studies, particularly those exploring scattering amplitudes, suggest that string theory might be an inevitable description of the universe, even if direct experimental verification remains elusive. Some physicists have even proposed new models of spacetime within a string theory framework that could explain the accelerating expansion of the universe and align with recent dark energy observations, potentially offering the first observational evidence supporting string theory. These models suggest that spacetime at the smallest scales behaves in a profoundly quantum way, where the order of coordinates matters, and this structure naturally gives rise to cosmic acceleration that decreases over time, consistent with recent data. The philosophical implications of a universe described by string theory are vast. The existence of hidden dimensions challenges our intuitive understanding of reality, suggesting a much richer and more complex cosmos than we perceive. It raises questions about the nature of space and time themselves, and whether our perceived reality is merely a projection of a higher dimensional existence. The ongoing debate between string theory and other approaches like loop quantum gravity highlights the diverse and innovative thinking currently at play in the quest for a unified theory. While LQG focuses on the quantum nature of spacetime itself, string theory investigates the behavior of objects within spacetime, offering a different yet equally profound perspective on the fundamental fabric of reality. Black holes represent the ultimate crucible for quantum gravity, environments where the exquisite predictions of general relativity push up against the baffling implications of quantum mechanics. At their heart lies the singularity, a point where classical physics breaks down, predicting infinite density and spacetime curvature. This is precisely where a quantum theory of gravity is desperately needed. One of the most profound challenges arising from this cosmic enigma is the black hole information paradox. Stephen Hawking's groundbreaking work in the 1970s suggested that black holes aren't entirely black, they emit a faint glow of particles known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where pairs of virtual particles are constantly popping into existence. One particle falls into the black hole, while its partner escapes as Hawking radiation. The problem is, Hawking's calculations indicated that this radiation is purely thermal, carrying no information about the matter that formed the black hole or subsequently fell into it. If a black hole eventually evaporates entirely through this process, as predicted, all the information about what it consumed would be permanently lost. This directly contradicts a fundamental principle of quantum mechanics called unitarity, which states that information should always be conserved. The black hole information paradox, therefore, highlights a deep incompatibility between general relativity and quantum mechanics, making it a guiding post for progress in quantum gravity. Both loop quantum gravity, LQG, and string theory offer potential avenues for resolving this paradox by providing a quantum description of spacetime at these extreme scales. In LQG, the singularity at the heart of a black hole, that infinitely dense point predicted by general relativity, is replaced by a quantum bridge or a bounce. Instead of collapsing to an infinite point, the spacetime fabric, being fundamentally discrete at the Planck scale, reaches a maximum density and then transitions into another region, possibly even a white hole that expels matter and energy. This pixelated nature of spacetime, where geometry itself is quantized into indivisible atoms or loops, prevents the formation of a true singularity. By eliminating the singularity, LQG suggests that information might not be truly lost, but rather preserved in the quantum structure of spacetime itself, perhaps emerging in a highly scrambled form during the black hole's final evaporation stages. String theory, with its vision of fundamental vibrating strings, offers a different, yet equally compelling, perspective. Within string theory, black holes are not simply empty regions of spacetime, but rather complex configurations of these fundamental strings, often described as fuzzballs. These fuzzballs are not singular points, but extended objects whose quantum states encode the information of the matter that formed them. The idea is that the event horizon, rather than being a smooth, featureless boundary, is actually a bustling, quantum mechanically rich surface. This holographic principle suggests that all the information contained within the three-dimensional volume of a black hole might be encoded on its two-dimensional surface, much like a hologram. When a black hole evaporates, this information, encoded on the surface, would be gradually released through Hawking radiation, thereby preserving unitarity and resolving the paradox. The quantum gravity effects in string theory are not confined to the Planck length, but can spread over macroscopic distances, such as the horizon radius, due to the large number of quanta making up the black hole. The concept of quantum pixels becomes particularly vivid in these extreme environments. If spacetime is indeed pixelated at the Planck scale, approximately 10 to the power of -35 meters, then near a black hole's event horizon and certainly within its interior, these quantum pixels would be stretched, distorted, and rearranged in ways that defy our classical intuition. The Planck length is the scale at which quantum gravity effects are expected to dominate, and it's precisely at this scale that the smooth, continuous spacetime of general relativity gives way to a granular, quantum reality. In regions of extreme density, such as the interior of black holes, it's theorized that these quantum pixels might be so tightly packed that they cannot activate or manifest spacetime in the usual way, leading to a fundamentally different understanding of what constitutes a black hole's interior. The firewall paradox is another fascinating offshoot of the black hole information paradox, further illustrating the tension between quantum mechanics and general relativity at the event horizon. It suggests that if information is indeed preserved and escapes a black hole, then an infalling observer would encounter a blazing firewall of high-energy particles at the event horizon, instantly incinerating them. This directly contradicts Einstein's equivalence principle, which states that an observer falling freely across an event horizon shouldn't feel anything unusual. The firewall paradox highlights the profound implications of demanding information conservation in the context of black holes and underscores the need for a complete theory of quantum gravity to reconcile these seemingly contradictory principles. Both LQG and string theory offer potential resolutions to this paradox by modifying the behavior of spacetime or quantum fields at the horizon. For instance, the fuzzball model in string theory suggests that the radiation emerges from the surface of the fuzzball, carrying information, and thus bypasses the firewall argument. The interior of a black hole, beyond the event horizon, is where quantum gravity effects are most pronounced and least understood. While general relativity predicts a singularity, quantum gravity theories aim to replace this with a more physically meaningful description. The larger a black hole, the longer it takes for gravitational effects to build up to a strength requiring a full quantum treatment for an infalling observer. However, eventually, the deep black hole interior necessitates a quantum theory of gravity due to the strong interactions between gravity and quantum physics. The very notion of spacetime itself might be fundamentally altered in these extreme environments, potentially leading to a computational event horizon where information is irreversibly lost to an incompressible computational process, leading to wave function collapse. The study of black holes, therefore, is not merely about understanding these enigmatic cosmic devourers. It's about pushing the boundaries of our physical understanding to the very limits of spacetime and matter. It's about unraveling the quantum nature of gravity and ultimately unifying the fundamental forces of the universe. The extreme conditions within and around black holes provide a unique laboratory for testing the predictions of nascent quantum gravity theories, offering tantalizing clues about the true, pixelated nature of reality. The Big Bang, as described by classical general relativity, presents a profound challenge, a singularity, a point of infinite density and temperature where the laws of physics, as we know them, break down. This is precisely where quantum gravity is expected to offer a more complete picture, suggesting a pixelated Big Bang, where the universe's origin is described not by an infinite point, but by the smallest possible units of spacetime. Quantum cosmology, a field that applies quantum gravity theories to the early universe, aims to describe the entire universe as a quantum system. One of the most compelling aspects of a pixelated spacetime is its potential to resolve the singularity problem. In theories like loop quantum gravity, LQG, the Big Bang singularity is replaced by a big bounce. Instead of collapsing to an infinitely dense point, the universe, in a previous phase, contracted to a minimum size, the Planck scale, where spacetime is quantized, and then bounced back into expansion, giving rise to our current universe. This concept fundamentally alters our understanding of cosmic beginnings, suggesting a universe without a true beginning in the classical sense, but rather a continuous cycle of contraction and expansion. The idea of a pixelated spacetime also has profound implications for the inflationary epoch, a period of exponential expansion immediately following the Big Bang that stretched the universe to immense scales in a fraction of a second. Inflation is crucial for explaining the observed homogeneity, flatness, and large-scale structure of the universe. In this scenario, tiny quantum fluctuations in the very early, microscopic universe were stretched to macroscopic scales during inflation, becoming the seeds for the formation of galaxies and clusters of galaxies we observe today. If spacetime itself is pixelated at the Planck scale, then these initial quantum fluctuations would arise from this discrete structure. Some new quantum gravity models suggest that cosmic inflation, rather than being driven by a hypothetical inflating field, could emerge naturally from the dynamics of a quantum theory of gravity, such as quadratic quantum gravity. These models also predict a minimum level of primordial gravitational waves, which could potentially be detected by future observatories, offering a direct observational test of these quantum gravity effects in the early universe. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, holds crucial clues about the early universe. Imprints of quantum gravity effects from the inflationary period, such as new massive modes beyond the massless graviton, could be detectable in the CMB's power spectrum. Some research within loop quantum cosmology suggests that the Big Bounce could leave specific fluctuations in the CMB that correlate with observed anomalies, offering a potential way to distinguish between different quantum gravity theories. Beyond the Big Bounce and inflation, the concept of a pixelated universe opens doors to even more speculative, yet fascinating, ideas about our cosmic origins. For instance, the notion of quantum tunneling from nothing proposes that the universe could have quantum mechanically tunneled into existence from a state of nothingness, where nothing refers to a vacuum teeming with quantum fluctuations. This is a highly theoretical concept, as quantum fluctuations are typically understood to occur within existing spacetime. However, if spacetime itself is emergent from a more fundamental quantum realm, then such a tunneling event could represent the birth of spacetime itself. Another intriguing concept is that of spacetime foam, proposed by John Wheeler, where at extremely small scales, spacetime isn't smooth but a chaotic, fluctuating foam of constantly appearing and disappearing virtual particles and mini-universes. This foamy texture, influenced by quantum fluctuations, could have played a role in the inflationary period, with the expansion stretching this quantum foam to cosmic scales and laying down the gravitational seeds for structure formation. Some models suggest that the degree of foaminess is dictated by black hole physics and is of a holographic nature, implying a connection between the information content of spacetime and its boundary. The holographic principle, a radical idea stemming from black hole thermodynamics and string theory, posits that all the information contained within a volume of space can be encoded on its two-dimensional boundary, much like a hologram. If applied to the entire universe, this suggests that our three-dimensional reality might be a projection from a two-dimensional surface. In the context of the early universe, this could mean that the initial conditions of our cosmos were encoded on some primordial boundary, with the expansion of the universe unfolding this information into the three spatial dimensions we perceive. Theoretical work even suggests that quantum entanglement could be the underlying mechanism for this holographic projection, with entanglement patterns at microscopic scales potentially weaving the fabric of reality itself and influencing the large-scale structure of the cosmos. These ideas, while highly theoretical and currently beyond direct experimental verification, offer tantalizing glimpses into a universe far stranger and more interconnected than our everyday experience suggests. The search for a theory of quantum gravity is not merely an academic exercise. It is an endeavor to understand the very essence of existence, to unveil the ultimate nature of spacetime, and to decode the primordial blueprint of our pixelated Big Bang. The extreme conditions of the early universe, much like the interiors of black holes, serve as the ultimate testing grounds for these profound theories, pushing the boundaries of our knowledge and hinting at a reality woven from quantum threads. The quest for experimental evidence of quantum gravity is one of the most formidable challenges in modern physics, primarily because the quantum effects of gravity are predicted to manifest at the Planck scale, an energy regime far beyond the reach of current particle accelerators. The Planck length, approximately 10 to the power of -35 meters, is an unimaginably small scale, about 10 to the power of 20 times smaller than a proton. However, Despite these immense hurdles, scientists are ingeniously devising experiments and observations that might offer indirect glimpses into the quantum nature of spacetime. One promising avenue involves searching for subtle deviations in the propagation of light and other particles from distant astrophysical sources. Some theories of quantum gravity predict that the vacuum of space, at extremely high photon energies, might behave less like a smooth, continuous medium and more like a foamy or pixelated structure. This could cause different frequencies of light to travel at slightly different speeds, a phenomenon known as Lorentz invariance violation. Gamma-ray bursts, GRBs, which are among the most energetic events in the universe and originate billions of light years away, serve as excellent natural laboratories for these tests. If high-energy gamma rays from a GRB arrive at Earth with a measurable delay compared to lower-energy gamma rays, it could be a signature of quantum gravity. For example, an analysis of GRB 2-21009A, the brightest gamma-ray burst ever observed, placed some of the tightest constraints on such violations, though no definitive difference in propagation speed was found. Nevertheless, future observations of even more distant and powerful GRBs could potentially reveal these elusive effects. Neutrinos, with their incredibly weak interactions, also offer a unique window into quantum gravitational phenomena. These ghost particles can travel vast cosmic distances, making them sensitive probes of any subtle alterations to spacetime. Some theoretical models suggest that quantum gravity could affect neutrino oscillations, the phenomenon where neutrinos change between their three flavors, electron, muon, and tau, as they travel. While experiments like ORCA, oscillation research with cosmics in the abyss, have not yet detected such decoherence, they continue to push down the upper limits of where these effects might be found, tightening the search for quantum gravity's influence on these particles. Additionally, some physicists have theorized that ultra-relativistic neutrinos blasted into space during gamma-ray bursts might be slowed down by quantum gravity effects, and there have been observations of neutrinos arriving later than their companion gamma rays, hinting at this possibility. Black holes, as extreme environments where both general relativity and quantum mechanics are essential, are considered prime natural laboratories for studying quantum gravity. While directly observing quantum effects at the singularity within a black hole remains impossible, scientists are exploring indirect signatures. For instance, the gravitational waves emitted during black hole merger events, now routinely detected by observatories like LIGO and Virgo, could carry information about the quantum nature of spacetime near these colossal objects. Researchers are exploring methods to characterize the quantum states of gravitational waves themselves, moving beyond simple detection of these ripples in spacetime. This includes the potential for detecting individual gravitons, the hypothetical fundamental particles of gravity, and analyzing their quantum statistics. Furthermore, black hole morsels, remnants of black hole mergers, are theorized to emit bursts of high-energy gamma rays with a delay related to their mass, providing a distinct, detectable signature that could offer direct experimental access to quantum gravitational phenomena. Gravitational lensing, the bending of light around massive objects, is another area where quantum gravity effects near black holes could potentially be observed, though these effects are subtle and analogous to electric charges in weak lensing, while exhibiting opposite behavior in strong field limits. Beyond astrophysical observations, a new frontier in experimental quantum gravity involves ingenious tabletop experiments designed to probe the quantum nature of gravity in controlled laboratory settings. Traditionally, the energy scales required for such experiments were thought to be astronomically high, 15 orders of magnitude greater than what current particle accelerators can achieve. However, recent advances in cooling, control, and measurement of mechanical systems at the quantum regime have opened up exciting possibilities. One of the most promising ideas involves testing whether gravity can generate quantum entanglement between particles. If two initially unentangled systems, interacting solely through gravity, become entangled, it would imply that gravity itself must be quantum. Experimental designs propose using nanoscopic masses with precise electromagnetic shielding and noise control to isolate gravitational effects. Such experiments might employ levitated diamonds, metallic spheres, or laser-cooled atoms, systems where both position and gravitational effects can be precisely controlled. For example, a technique developed at MIT uses laser cooling to bring centimeter-scale torsional oscillators to quantum states, bridging the classical and quantum worlds and enabling new experiments to test gravity's quantum nature. Another proposal suggests examining gravitational interactions between harmonic oscillators, such as pendulums. Calculations show that for weights around 100 milligrams and distances of a few microns, quantum gravitational effects could cause pendulum oscillations to become slightly chaotic and random, a measurable deviation. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, also holds clues to quantum gravity. Loop quantum cosmology, for instance, suggests that repulsive gravity at the quantum scale in the early universe could have smoothed out inhomogeneities, which would leave an imprint on the CMB. While some quantum gravitational corrections to the CMB anisotropy spectrum have been calculated, they are currently too small to be detected. Nevertheless, ongoing and future CMB experiments, such as SPT, 3G, and the Simons Observatory, are continuously improving their sensitivity and angular resolution, aiming to extract even more cosmological information and potentially uncover subtle signatures of quantum gravity from the earliest moments of the universe. The pursuit of experimental evidence for quantum gravity is a testament to humanity's relentless drive to understand the fundamental nature of reality. From the most distant corners of the cosmos to meticulously controlled tabletop experiments, scientists are pushing the boundaries of technology and ingenuity, hoping to finally unveil the quantum threads from which our pixelated universe is woven. The notion of a pixelated universe, where space-time isn't a smooth, continuous canvas, but rather a tapestry woven from discrete, indivisible units, carries profound philosophical implications that challenge our most fundamental assumptions about reality. This shift from an analog to a digital cosmos would represent a revolution in our understanding of existence, akin to the discovery that matter is composed of atoms. One of the most immediate consequences of a pixelated spacetime is the idea of a fundamental limit to information density. If space and time are discrete, then any given volume of space can only contain a finite amount of information, a finite number of bits. This resolves long-standing paradoxes, such as the black hole information paradox, which questions what happens to information that falls into a black hole. If the universe is digital, information cannot truly be lost. It must be conserved, perhaps encoded on the black hole's two-dimensional boundary, much like a hologram. This holographic principle suggests that all the information about a three-dimensional volume of space could be encoded on its two-dimensional surface, implying that information itself is discrete, like pixels on a screen. A pixelated universe also offers a novel solution to ancient philosophical problems, such as Zeno's paradoxes. Zeno of Elea argued that an arrow in flight could never reach its target because it would first have to travel half the distance, then half of the remaining distance, and so on, infinitely. In a continuous space-time, this infinite divisibility poses a genuine conceptual hurdle. However, if space and time are pixelated, there's a smallest possible unit, the Planck length and Planck time, below which further division is impossible. This means the arrow does reach its target by traversing a finite number of these fundamental pixels, effectively sidestepping Zeno's argument. The idea of discrete spacetime challenges our perception of continuity. What we experience as smooth motion and an unbroken flow of time might, at its deepest level, be an illusion. Much like the continuous motion we perceive on a digital screen is actually a rapid succession of static images. This raises questions about the nature of change and becoming. Some interpretations of loop quantum gravity, for example, suggest a radical process metaphysics where there is becoming and change, but not necessarily being in the traditional sense of enduring substances. In this view, the physical world could be timeless yet ever-changing, a profound reevaluation of how we understand existence. The philosophical implications extend to the very nature of our perception. Even if reality were continuous, our sensory organs and brains process information discretely. Our eyes sample light with rods and cones, our ears break sound into vibrations, and our brains compress and edit this data. So, in a sense, our experience of reality is already pixelated at a biological level. The question then becomes whether this is merely a limitation of our perception or a reflection of an underlying discrete reality. The concept of a pixelated universe also resonates with the simulation hypothesis, which posits that our reality could be a computer simulation. If space-time is discrete, with a fundamental limit to its resolution, it makes the idea of a simulated universe more plausible, as all existing simulations are, by their nature, pixelated. This doesn't necessarily prove we live in a simulation, but it certainly lends a new dimension to the discussion, blurring the lines between physics, philosophy, and even theology. The question of who set the resolution, a god, a programmer, or a cosmic law, becomes a profound inquiry. Furthermore, the implications for our sense of identity are considerable. If the world is pixelated, could we, too, be fragmented, ourselves assembled from snapshots, our histories cobbled from fragments, our morality provisional? This realization can be both liberating and terrifying, challenging our ingrained longing for continuity and wholeness. The pursuit of quantum gravity, through theories like loop quantum gravity and string theory, inevitably pushes us into the realm of metaphysics. Loop quantum gravity, in particular, has been noted for its philosophical underpinnings, often drawing on philosophical reasoning from first principles and engaging with foundational issues that many physicists traditionally shy away from. String theory, while often seen as more mathematically driven, also grapples with profound philosophical questions, especially concerning the nature of a final theory and the implications of concepts like the multiverse. Ultimately, whether space-time is truly pixelated or smoothly continuous remains an open question, one that experimental physics is striving to answer. But the very act of contemplating a pixelated universe forces us to confront deep philosophical questions about the nature of reality, information, time, and even our own existence. It compels us to re-examine what we mean by real, and to consider that the seamless, flowing world we inhabit might be a magnificent, emergent illusion, woven from the most fundamental and discrete threads of the cosmos. The quest to unify the cosmos, to weave together the disparate threads of reality into a single, elegant tapestry, remains the ultimate ambition of physics. We stand at a precipice, looking out at a landscape where the grand, sweeping curves of general relativity and the erratic, probabilistic dance of quantum mechanics stubbornly refuse to fully align. This incompatibility, particularly under extreme conditions like those found in black holes or at the universe's origin, signals a profound gap in our understanding. The future of physics is fundamentally about bridging this divide. Theories like loop quantum gravity and string theory represent our most promising, albeit radically different, attempts to construct a quantum theory of gravity. Loop quantum gravity posits that space-time itself is quantized, a discrete network of interwoven loops, suggesting a granular, pixelated reality at the Planck scale. String theory, on the other hand, proposes that fundamental particles are not point-like, but rather tiny, vibrating strings existing in higher dimensions, with gravity emerging naturally from these vibrations. The challenge lies in the lack of experimental evidence to decisively favor one over the other, or indeed, to confirm any quantum gravity effects at all, as these effects are predicted to occur at scales far beyond our current observational capabilities. However, the pursuit continues with relentless ingenuity. Researchers are exploring novel avenues, such as rethinking fundamental concepts within existing theories. For example, some physicists are investigating whether particles might deviate slightly from the paths predicted by classical relativity when moving through a quantum spacetime, offering a potential observable effect. Others are exploring frameworks that attempt to unify quantum mechanics and classical gravity without necessarily requiring a quantized description of gravity itself, suggesting a stochastic or random coupling between the two. These diverse approaches highlight the dynamic and open-ended nature of this scientific endeavor. The integration of artificial intelligence is also poised to revolutionize theoretical physics. AI can analyze incredibly large datasets, such as those from particle physics experiments, and identify patterns in mathematical models and simulations that might otherwise be missed by human researchers. This could accelerate our ability to solve complex equations and simulate intricate physical systems, potentially leading to breakthroughs in quantum gravity and cosmology. Beyond the theoretical and computational, the search for a unified theory is deeply intertwined with our understanding of the universe's most enigmatic components, dark matter and dark energy. These mysterious entities constitute approximately 95% of the universe, yet they remain outside the standard model of particle physics. A true theory of everything would ideally shed light on their nature, perhaps revealing them as particles from hidden dimensions or as manifestations of the quantum structure of spacetime itself. Cosmological studies, particularly those focusing on black holes and the conditions of the early universe, will continue to provide crucial insights and constraints for these unifying theories. The philosophical implications of a pixelated universe are profound, touching upon the very essence of existence. If space-time is fundamentally discrete, it challenges our intuitive perception of a smooth, continuous reality. This idea, reminiscent of ancient philosophical debates about whether reality is continuous or composed of indivisible units, suggests that our everyday experience might be a magnificent emergent property, much like a high-resolution image composed of countless individual pixels. It compels us to re-examine what we mean by real, and to consider that the seamless, flowing world we inhabit might be a magnificent, emergent illusion woven from the most fundamental and discrete threads of the cosmos. This perspective opens up fascinating questions about the nature of reality, information, time, and even our own existence. It compels us to re-examine what we mean by real, and to consider that the seamless, flowing world we inhabit might be a magnificent, emergent illusion woven from the most fundamental and discrete threads of the cosmos.